Hey everybody, how you folks doing today? Happy Tuesday. All right, we're going to talk about recursion today. It's technically a little bit out of order, but that's okay. Inheritance comes first, but that's no big deal. You know what, actually, I can even change that too. I could redirect, that's okay. So I'm going to talk about recursion first, and then we'll talk about inheritance on Thursday. We'll do our lab on Monday, and then we have one last week of class. Holy cow. So we'll talk about plotting and some basic graphics this last week. And then our final presentations are 12:13. 3 to 6 p.m. is our slot here. So that's a little bit funky, the 3 to 6 slot. I don't think we'll need that whole time though. Let's double check here. Come on, calendar. There we go. So that's a Monday here, not a Tuesday or Thursday. So that's essentially our lab time, right? Kind of smack in the middle of our lab time, Monday, 3 to 6 p.m. So there's no lab on plotting or basic graphics. Don't worry too much about it. We can touch more on that next semester if you continue on in 2001 here. But that's the plan here. So you'll do our final project presentations. I'll send out a Zoom link and we can go from there. That sound like a good plan? All right, just checking, see if anyone's actually online. Yeah, we got a couple people. All right, awesome. So before we jump into recursion, did you want to talk about any of the labs that we'd worked on? I think that was, we were kind of getting in the habit of talking about the labs, but did we get all caught up with the labs? We had our exceptions and modules lab. We haven't talked about that one yet. We can if you'd like, but just let me know. I'm open to either. No preference? That's okay. All right, let me zoom this in a little bit here. So recursion all by itself is actually a relatively straightforward topic. Oh yeah, lab 8, you got it, Bay. So lab 8, oh, that's the, yeah, that was exceptions and modules, right? Yeah, our exceptions and modules. Let me pull this one up here. Start with a new project for that one. So we're going to build this module with our two functions here. This financial module is going to have a number of payments and a payment amount as two functions. Then we're going to write. And we're going to include value errors if something was wrong with those parameters that were given to us. So let me start up a new, oh, I got main here. So we're going to add a new module, a Python file. That's all module is just another file. We'll call this financial. And we're going to have those two functions. We have the number of payments and the payment amount. We'll define number of payments, and that needed three things, right? It needed the rate, the payment amount, and the present value. So it was the rate, and typically this was an annual rate. So if you wanted to call it annual rate so you knew, that'd be fine. And then we wanted the payment amount. And then we wanted the present value. And really, present value is like, how much do you owe on the loan? Right? It's essentially the loan amount. So if you want to call that one loan amount, that might work too. All right, so the idea is we're going to apply the interest, right? And we typically do this in monthly. This is kind of funny how all this works, but you do a monthly payment. So the annual rate, we have to divide by 12. So we're going to take the loan balance. Is going to start off as the loan amount. And then we're going to loop while my loan balance, come on, type that, there we go, is greater than 0. Right? So then we'll have a number of payments here. Number of payments is going to start off at 0. And every time we loop then, right, we're going to take our number of payments plus equal 1. We'll add 1 to it. We're going to take our loan balance, and we're going to add to it the loan balance times the annual rate divided by 12, right? Because that's the monthly rate. So take the balance, apply the monthly rate. So if it's 3% interest, right, that'd be 1/4%. So you pay 1/4 of 1%, of interest get added to the loan, and then we'll take our loan balance and we'll subtract the monthly payment amount. And this just keeps on going until our loan balance is no longer greater than 0. So a couple things. We're going to have a value error if the rate is not greater than or equal to 0 and less than 1. Right? So that rate here, we don't want it to be 6 if you mean 6%. 6% should be 0.06. So we can check on that real quick. We can do a quick check and say if the annual rate is 0, less than the annual rate, it's less than 1. Right? So this is the good version here. Right? If it's greater than or equal to 0 and less than 1. So greater than or equal to 0. Greater than or equal to 0. So really, we don't want either of that. We want the opposite. So if its annual rate is less than 0, or the annual rate is greater than or equal to 1. That's the case then. So we want, if this is true, right, either one of these, it's invalid, we'll raise a value error. Raise value error. Annual rate must be between 0 and 1. Okay, that's our first check. Then we're going to raise a value error if the present value is less than 0. Right, so if you try and give me a negative balance for that loan amount, the present value, it's going to mess things up. So if the loan amount is less than 0, we'll raise a value error. Loan amount must be greater than 0. Right, I guess really even less than or equal to 0 is probably fine. Either one should be okay. All right, and then we'll have our loan balance. We'll have our number of payments. We'll increase our number of payments. Keep on going here. And then when we're done, we're going to return the number of payments. Why does it not like that? Oh. Shadows number of payments from outer scope. Oh yeah, we don't want it to be called that. That's probably no good. So this is, we don't want the same name as our function. That's going to get confusing. So how about we call it payments? We'll just call it payments. That'll work. Okay. And there we go. So that should return how many payments it took. Okay, the next one was the payment amount. Now this one was an easier formula here we could do. So the payment amount given a rate, number of payments, and a present value. So kind of the opposite of this one. Right, this is telling me how long it's going to take to pay off. The other one says, hey, how much do I have to pay if I want to pay it off in this amount of time? Is my payment amount given an annual rate, a number of payments, and the loan amount. Or again, present value. Either one's fine for that. No big deal. Doesn't like that one either. That's okay. I think no, we should use someone else. Payments. We'll try payments. Okay, so then we have a formula for this one. CaptainCalculator.com. Look at that. Present value times the present value plus the future value. We don't have. Right, so that was not there. We're not doing anything with future value. It's going to be 0 divided by 1 plus the rate to the n, right, number of periods, minus 1 times negative rate divided by 1 plus b here. And this was going to be, b was 0, right, because we didn't need to worry about that. So there's going to be at the end of the period is the easier one. So times negative r divided by 1 plus 0 is just negative r, right? So a couple of things in here. We should be able to get this. So present value is the loan amount times the present value plus the future value. It's still just going to be the present value because it was 0. Right? This was times divided by 1 plus the annual rate divided by 12, right? Because then the n was my payments. So that was to the power of, right? minus 1, where so that one happens first, and then we subtract 1 from it. Okay. Should be good. Times the negative, this is annual rate, divided by 12, divided by 1 we don't need. Let's see if that does what we want for us here. I should slide this over. It's getting kind of long there. This will be the payment equals loan amount times the loan amount divided by 1 plus annual rate divided by 12 to the number of payments minus 1 times the negative annual rate divided by 12. Let's see if that works. Now we also needed to check in here then. Right, raise a value error if the rate is not greater than or equal to 0 or 1, and then present value is less than 0. So same errors as above. I'm just going to copy those same ones. Okay. And another file, import the module, use the functions to allow them to calculate payments or number of payments. Be sure to use our try and accept block to handle any errors. Okay, so that's in our main then. Now to import financial. Right, if we wanted to say from financial, right, we could import the specific functions, but now it's just financial dot, right, number of payments or payment amount. So we can ask them, right? We'll just print. I guess we'll get their choice here. Their an input of you want to calculate the number of payments or payment amount, and then maybe it would like I don't know n for number of payments, like or p for payment amount or something. To some sort of visual cue to like tell them what we want them to enter. Okay, and if the choice is equal to n, and probably right 2 lower or 2 upper, choice dot upper, right? I'll do that one. I'll if choice dot upper equals p, then we'll do that one. Right. Otherwise, we'll print. I can't do that. Sure. Hey, Hector, thank you so much for sharing those bits, supporting the Student Scholarship Fund here at the University of Michigan Dearborn. That's so cool. And it is Giving Tuesday, by the way, so I'm sure they'll be hitting you up for donations. All right, so for number of payments, then, we needed those 3 pieces of information, right? So we needed the rate, annual rate, equals probably a float of an input, right? What is the annual rate? 0 to 1. And then we'll have the payment amount. Payment amount equals, again, probably a float, why not, of an input. What is the payment amount? And then we'll have the loan value. Loan value. That one's probably an int, but we're doing floats, so why not do a bunch of floats everywhere? Input is the loan amount. And we'll calculate it. We'll call financial. This will be the number of payments. We'll just call payments, right? Payments. My financial module. Dot number of payments, given the annual rate, the payment amount, and the loan value. Loan value. Oh, it should have been loan amount, right? Loan amount. Sure. Okay, and then we can print out. It will do that as a little formatted string. Right, payments. You pay off the loan. Okay, same idea then for payments here. Annual rate instead of payment amount, this is the number of payments, right? So payments. How many payments? How many payments are you making? what's the loan amount, and then this would be the payment amount then. Given the payment amount, given the number of payments. You'll have to pay, right? You will have to pay the payment amount, monthly. All right, let's try it. See if it works. So give it a run. All right, so let's do, how about the payment amount first? So if the rate is, say, 3%, right? So 0.03 is 3%. How many payments are we making? If we make, let's do 12 payments, and the loan amount is, we'll say, $1,000. Uh-oh. Did we forget to return? I think we forgot to return. Yep, we forgot to return. Return payment. There we go. Make sure we hit the return there. And then we also forgot to do all of this in a try-catch block, right? So we need to try this and catch as a value error, right? Or accept value error as E. We'll print the error. Sure. Do a try. Put this in our accept block. Accept the value error as E. Oh, we can print out the error if something bad happens. All right, let's try one more time. All right, so payment amount. If we have a 3% loan and we're going to make 12 payments and we're going to borrow $1,000. Uh-oh. That doesn't look like the right number. Must have a parenthesis out of order. Let's take a look. What did I do wrong here? Let's double check. Present value times present value plus future value divided by 1 plus the rate to the power of n minus 1. Let's make sure we plug this in right. Yeah, minus 1, right? Are those parentheses in the right spot? No, they're not. They're not. So one more parenthesis there. Right? No. Oh no, that one's right. 1 plus the annual rate divided by 12 to the power number of payments minus 1. That ought to be it, right? Times negative rate divided by 1 plus, yeah, we're doing it at the end. Why is that not working for me? So, oh, per period then, so it's going to be 0.0025, right? Instead of quarter. 12 payments. Should be 83. And what do we get? Too large of a number. -1 times the annual rate? I think negative. Negative should have done it, right? Divided by 12. Oh, we need the parentheses on this last one here. Let's try that. Should be the same. Let's try it again. See what we did wrong here. Oh, that one doesn't run, right? This one runs. All right, payment amount. We said 0.03 annual, 12 payments, $1,000 loan. Still wrong. My goodness. 82, 335. Did our payment? Loan amount. Oh, is this plus? Wait, they have a plus in all of their calculations here. Not a multiplication. Is that a typo? Is that plus? Let's see if it's plus. $0.03. That was another. Oh goodness. No, I wanted. Yeah, payment amount. I did the wrong thing. Restart. All right, number of payments. Payment amount for a rate of 3%, 12 payments, $1,000 loan. Nope. That was no better. Where did that go wrong? Amount divided by, and 1 plus the annual rate divided by 12 to the number of payments, minus 1 times our annual rate, negative annual rate divided by 1, so it did nothing there. I'm not sure, folks. I'm not sure. Did you get it to work, Bay? That should have done it. Let's see. Maybe I have the wrong formula. Oh, let's see. Calculate payment on loan balance. See if we get a different hit. I think that was our first hit. Is that the money calculator? Is that the same one? Nope, that's okay, this is a different one. Where's the formula? I want the formula. Oh my goodness. That's why. Formula. The balance. Try this one. No, sorry, Bay. I thought I got the right formula there. Let's see. So this is the loan balance divided by, let's see, is this one any easier then? So it's our loan balance divided by 1 plus the rate to the power, number of payments, minus 1, divided again by the rate times the rate. Okay, let's try that formula then. So that was going to be the loan amount divided by our 1 plus the rate to the power of number of payments divided by 1 plus, this was our annual rate, divided by 12, right? To the power of payments. Right, that was the first one. Divided that again. Oh, then minus 1 on that. Why is that minus 1? That's funny. Minus 1. Divided by the payment, or the rate times rate to the number again. Okay, sure. Divided by, this is our annual rate, divided by 12 times 1 plus annual rate to the number of payments. Let's see if that one works any better. Sorry about that. I didn't realize that would be so much trouble. Let's see. The payment amount, 0.03, so 3%, making 12 payments on $1,000. Nope, that's still the wrong number. What the heck? Loan amount divided by the rate times still giving us the wrong number. I don't know what I did wrong here, folks. I'm sorry. It's must be something here with our formula. 1 plus the rate to the number of payments, minus 1, divided by again. That one's different than this one, right? Divided by and times. No, the formula works if we get the right formula there. Is that... Am I not supposed to divide again? This one has dividing again. This one has multiplying by the negative rate. I'm super confused. Let me try one more thing here. I'm gonna look it up on my other screen here. We'll see if that works. Let's see. See if I can find it here. Just 1 second. Nope, don't have it there. Shoot. Oh, maybe I have it. Nope, I don't. Come on, when did I do this? Nope, I only had part of it done the other time. No, I'm not sure. One more look, one more try. Formula, calculating loan payments. We'll get it. We'll get it here. WikiHow, this has got to be it. WikiHow. It's got to be good here. No, we don't want an online calculator. Manually, this is what we want. Okay. M is P, our principal, times J divided by 1 minus 1 plus J to the negative N. Okay? All right, let's try that. Let's try that formula. Why do they use such terrible letters? They use such terrible letters. All right, so P then is going to be our loan amount. So let's do the, how about monthly rate is our annual rate divided by 12. Let's make that a little easier here. There's our monthly rate. 1 plus the monthly rate to the power of negative payments. Okay, I think we plugged all that in. I'm going to cross my fingers. Let's try it. All right, payment amount. 0.03, 3%, making 12 payments on $1,000. Look at that, 84. Hey, we found a formula that works. All right, I'm going to update my notes here because this one actually worked. My goodness. My goodness. Come on. Load. Let's go canvas. All right. So we will change that one to... Nope, nope. Oh, goodness. That really... I don't need any of that, right? There we go. WikiHow calculated loan payments. That ought to do it. All right. Solved. Let's go save this. Stretch. Yeah, thank you, Bay. That's right. After working that one out. Oh, there we go. Woo. So now let's see if that works then. Let's run it one more time. Let's plug in that opposite here. So the number of payments then, if we had a 3% rate, if we wanted to pay, what was that, 85 essentially, and the loan amount was $1,000, it'll take 12 payments. So our two formulas agree. Man, I like this one better too. That's nice. Take out those extra parentheses. Okay. All right. That was fun. Let's commit that one. And now it's solved for next time. Look at that. Alrighty. 1501. Let's go. Here's lab 8. All right, we don't need any of the recursion stuff yet. I'm going to wait to commit those. Boop. All right, commit. Uh-oh, I'm lagging. Oh dear. I'm asking my computer to do too many things. I'm sorry. Come on, GitHub. All right, commit and push. Got it. All right, let's go back to the Recursion project now. All right, so with recursion, it's actually a relatively simple idea. We're not going to do too much with it. Again, this is a core topic we'll talk about next semester as well. But the simple definition of recursion is a function that calls itself. So like we might have the simplest one we can think of probably here is a countdown for number. Now, when it comes to recursion, you have to have two things be true. The first one being you have to have a case in which we'll call the base case, which is solvable and done. Right? If you give me this parameter, I know the solution, I'm done. That's the base case. The other thing you have to have is a way to take something that's not the base case, we'll call it a complex case, make it simpler, break it down, make it approach the base case. And that might sound a little funny until we look at some examples, but in this case we'll say if countdown, or if the number is less than or equal to 0, we're done. Right? That's it. This is the end here. So we're going to count from a number down to 0. So if we get to less than or equal to 0, we're done. Actually, let's say less than 0. Because 0 is good. So really, we actually want the opposite. We want if it's not less than 0. So if it's greater than or equal to 0, what we're going to do, we're going to print the number. And then we're going to call countdown. Again, we're going to call ourselves given number minus 1. So this function will call itself with whatever number minus 1 if it's greater than or equal to 0. So once we hit 0, we'll print number. Right? So if we then say, how about countdown of 10? right? What's going to happen is we're going to call it at 10. 10 is greater than or equal to 0. It prints 10. It says, okay, call it itself again with 10 minus 1. We'll get 9. 9 is greater than 0. Print 9. Call it with 8. Call it with 7. Call it with 6. 5, 4, 3, 2, 1, 0. Call it with negative 1. Negative 1 is not greater than or equal to 0. It's finally done. So let's give this a run. We'll see. We can count down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now, a funny thing about recursion is that anything you can do recursively, you can do iteratively or without recursion. So, but sometimes there are problems that are more easily solved with recursion. And we'll get to some of those probably next semester. So we'll look at a couple ones, a couple different examples here of recursion, but we'll dive a little deeper again next semester. But this is just a real basic recursion here. Now, I'll take that one out. Now, you might have heard of the Fibonacci sequence. Does that ring any bells for Fibonacci? Fibonacci, I think there's 2 I's in it. Given the nth number in a Fibonacci sequence, right? So it's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, on and on and on. So it's the 2 previous numbers make up the next number. So we know if nth is equal to 1 or nth is equal to 2, then we can return 1. So this is our base case here. This is the simplest form here. If you want the first or second number in the Fibonacci sequence, I know it's a 1. And really we could say then really if nth is less than or equal to 2, we'll just give you back a 1. So if you ask for like 0 or negative or something, we'll just give you a 1 anyway, because we don't really care. So that's our base case. If it's not that, right, what I'm going to do is I'm going to return Fibonacci of nth minus 1 plus Fibonacci of nth minus 2. That's it. We've now solved the Fibonacci equation. We've done it in code. Now, there's actually a problem with this one here. And we'll get to that in a second. So let's say for value in range, let's go, I think 50. Let's print Fibonacci of value. Right? So let's go get all the fib numbers, right? And maybe how about we print, let's do a formatted string. So the f of this. So it'll tell me which number and what the value is. And actually, let's start at 1. Because 0, I'm going to pretend 0 doesn't count. Okay, so let's give this a try. Let's see what we get. Oops, we want value. Value. There we go. Didn't have enough. So you notice it spits them out pretty quick, right? 1, 1, 2, 3, 5, 8. But now it's getting slower and slower and slower. It works, but it's really slow. So what's happening here is we've done a kind of a bad thing, because every time you want a Fibonacci number, it needs to go all the way back down to 2 or less. So we're literally adding up 1. Here we got to adding up 1 14 million times. We added 1 to get to this, because the only value you can ever get is 1. So this is a really inefficient Fibonacci sequence here, right? It's not a very helpful Fibonacci sequence because it's so slow. It does way more work than it needs to. And where this is actually really easy as a loop here. So we'll define this is iterative fib given an nth value. We're going to say if, again, we can do the same one here, right? We can just check. Otherwise, right, we'll have a current nth equals, so we start at 3, right? And we'll have a previous is 1, we'll have a current is 1. So the previous value is 1, the current value is 1, our current nth is 2. Okay? And we can say while my current nth is less than nth, we want to keep on going. Less than or equal to the nth, right? The nth that you ask for. We want to keep on going. We'll have the next is equal to the previous plus the current, right? And then the previous will become the current, and the current will become the next. Then we'll take our current nth plus 1. What's up, Journey?
Where's the black and paper screen?
I don't know. It should be in the bag. It's in the laptop bag.
2 minutes and
It's in the laptop bag.
I don't know.
The laptop bag was in the back room. Go look in the back room, please.
Okay.
All right, so this way, then we're going to calculate counting up. Right, so if you want nth of 3, current nth was 2. Let's increase that. Just less than. Right, so we'll get the next, and when we're done, we're going to return current. So let's see if this one works for us here with iterative fib. And this one should be a lot faster here because it doesn't need to count up a bunch of ones. Look at that. We went up 1, 1, 2, 3, 5, 8. Yep, it looks like it's going here. 2, 3, 5, 8. So going up to 49, right? We solved that one pretty quick. That's how do we get the point comma in there, right? Do the comma? I forget. There's a way to format. Yeah, there we go. Yeah, comma separated. So 7 billion, pretty quickly there, right? Not too shabby. So this one's a lot faster, right? Because anything you can do recursively, you can do iteratively. Sometimes it's a little bit harder. So in this case, it's essentially just a loop. Loops are really easy to do here. Now, there's a case which is not faster here. This is called the Towers of Hanoi. Visualization. So the idea with the Towers of Hanoi is, there's a website for it. Is it this one? Maybe it's this one. Yep. The idea is you have to move disks from one peg to another. Oh, let's do 5 disks here. Is that going to do it for us? Here we go. So there's 5 disks, and the idea is you can't put a smaller disk, or you can't put a bigger disk on top of a smaller disk. So to move all 5 from this peg to this peg is difficult, right? That's not the base case. We don't know how to solve that. I don't have the cord. It's in the laptop bag. I don't have it. You guys had the cord last. So what's easier, though, is to move 4 disks to this peg, move the 5th disk here, and put the 4 disks back on top. That's the simpler solution. Well, it's actually hard to move 4 disks. It's easier to move 3 disks to this peg, move the 4th disk here, take the 3 disks here, put them back on top of the 4th. Well, moving 3 disks is hard, so let's move 2, move the 3rd, right? And the easiest case is to move 1 disk. So if we show the solution, it's just going to keep alternating this pattern of moving 2, and then moving 3, and then moving 4, and then moving all 5. So we're just going to keep repeating how to move 3 then. We'll do here. And then to move 4, we move the 4th disk, and then repeat the move 3 on opposite poles. So now we have to move 2. All right, we moved 2 to that pole. Now we can move the 3rd disk back on top of the 4th. And then we'll move the first 2 disks back on top of those. Then we'll move the 5th disk to the center pole, and then we'll repeat the move 4 to the center pole. And to move 4, well, we have to move 3. To move 3, we have to move 2. To move 2, we have to move 1. And we just keep on alternating. So this one is very easily solved with recursion because the way that you'd have to write your code to be able to do this pattern is not just a simple loop. There's not a simple loop we can write. There's just a quick little while loop that does this. It's much more complex to solve this Tower of Hanoi solution. And it's actually really easy to do in Python. So if we just search Python Tower of Hanoi, actually not very much code. Geeks for Geeks, look at that. First link here. Let's see if we got it. This is it. So given which number, what source, what destination, and what's the holding location, we're just going to keep repeating. Right? So if it's 1, we do 1. Great. If it's not, we do -1, and we flip the which is our holding pole, which is a destination pole. And then we move that one, and then we repeat again to put those other ones back on top. Right, give me just a second. I gotta go find that power cord that my daughter lost. Be back in just a moment. Alright, folks, sorry about that. Alrighty, let's finish up our recursion here. What's going on? Yeah, we got our Towers of Hanoi already. Come on. So again, that's something we'll talk more about next semester. In those cases where recursion is easier than just writing a loop here. But just some basic recursion here. We're just doing some loops. And there's one last one we're going to look at, and that is a search here. So this idea that if we have a sorted list here, so this is our, we'll call it a binary search, given a sorted list. So what we do with this idea of a binary search and a list is if you give me a list of, open a word here, list of values, and we put them in sorted order, I can try and find a given value in that list really, really, really quickly. Let's pull this up. Okay, look at that dark mode and everything. Thank you, Word. So if you give me a list of values here, and we sort them. So like 3 and 9 and 15 and 21 and 34. Okay, what we're going to do is we're going to take the middle of the list. In this case, we have a middle here, and we're going to see if the value is there. If the value is there, great, we found it. If it's not there, if it's less than, we're going to take half, and we're going to repeat the pattern with the half that's either less than or greater than. And we keep on going. So the binary search splits the difference every time. Like the guess 100 game, you guess 50, and then you guess 75 or 25. You keep splitting the difference. We're just doing a binary search in a sorted list here. Same idea. So to do that, we need a little bit more information. So we have the list, and then we have the value to search for. Search for. So the first thing we need to do is we need some additional information. So a lot of times when we have these recursive functions, we're going to have a public function that uses a private helper function here. So we're going to define a binary search. Again, with this private mark here, so we have the sorted list, we have the value to search for, and we have the start index, we have the end index. So at the beginning, then, we're going to just call this, we'll call return my helper binary search, given the sorted list, the value to search for, and then my start index is 0, and the end index is length of my sorted list minus 1, right? Because there's no actual index at the length here. The index is at length minus 1. Okay? So we don't want whoever's asking for a binary search to have to give me 0 and the length minus 1. We want to give them a nice, easy-to-use public method. Okay? So then we're going to look. So we need to find the mid. So our mid is going to be the start index plus the end index divided by 2. Right? That's the middle point. And we want floor division here. We want to make sure that we don't have decimal places, right? Because you can't have a half of an index. Indexes have to be integer values. So this integer division here, we'll make sure we have that. Okay? Then we're going to check. We're going to look at the sorted list. We're going to say if the sorted list at the mid is equal to the value to search for, then we're going to return the mid. We're going to return the index in which it was found. Otherwise, if that value is less than, oh, sorry, we don't need the parentheses there. Oh, gotta sneeze. Sorry about that. If that value is less than the value we're searching for, let's flip these around. Actually, I think it's easier to flip these around. So the value we're searching for is less than the midpoint. Then we need to search the other half. So if it's less than, we're going to return my binary search given the sorted list, given the value to search for, given the start index is the same, and now the end index is mid minus 1. So we've already looked at mid, so now mid minus 1 is where I'm going to look as the new ending index. Okay, and then if the value to search for is greater than the sorted list at mid, really, I guess this could just be an else here, because we know if it's equal, less than, and if it's not less than, it's got to be bigger than. So how about we just do an else? Let's make that an else to be easy here. We're going to do the same idea, but then the start will change. So it's going to be my start index plus 1 up to the end index. We'll search there. Now, we haven't found a base case yet, though, right? What is the simplest way in which we know there's a solution? Well, it's possible we found it. There's one. The other thing that might happen is if the start and end pass each other. Then we know we haven't found it. So even before this, then we can check. We can say, hey, if the start index is greater than the end index, then return, we're going to say -1, can't be found in the list. Or we could raise an error, right? I think the regular find raises an error here. Hey, KMP, how you doing today? So we'll just give you back a -1. This is, not found in list. Otherwise, we'll go see if we can find it here. We'll see if we can do it. So if we have a list of values, so we have some values is, 1, 3, 6, 9, 15, 21, 35. Sure. Why not? And then we want to print the binary search given my values, and we want to find, say, 7. We should get back a -1. Right? But if we wanted to find, say, 21, we should get back, this is 0, 1, 2, 3, 4, 5. Should be index 5. And then let's try, can we get back a 1, and let's try a 35. Right? See if we can get back all the, let's do 7, and then we'll just say for value in values, print binary search. I heard about that. Not really a big sports ball person myself, which is, I don't know. I played football in high school for a couple years, not my senior year because I ended up getting a job, but I just find it terribly boring to watch. But that's just me. And if you want to search for the value, then we should get out which index is that. So it should be 0, 1, 2, 3, 4, 5, 6, 7. Right? Maybe we'll do a nice little printed string here, formatted string. So let's say found the value at index. There. Okay. Let's see. So this should be a -1, right? We should not have found it. And then we should find all of them. Uh-oh. Oh dear. Single quote to end it. There we go. Single quote, not a double quote. So -1, yep, and then found 0, 1, 2, 3, 4, 5, 6. Looks good. So our binary search is working correctly. This idea of, right, we're splitting the difference. Again, we could do the exact same thing in a loop, right? It doesn't need to be recursion here. The loop here is a little bit trickier in this case because we're changing start and end, but it's still not the worst case here. So we can define a iterative binary search given a sorted list and a value to search for. Search for, and then we just have to keep that ourselves, right? So we're going to have a start index 0 and end index is the length of sorted list -1, and we can say while my start index is less than the end index, less than or equal to, right? We want to keep on going, right? We got to find the middle. We'll have mid is the same thing here, right? So mid is the start plus the end, floor divided by 2. If we found it, return mid. Otherwise, let's see if it's too high or too low. So instead of returning that value, right, we're just going to take we'll say the start index stays the same, but now the end index is going to be mid -1. Otherwise, it's the start index that changes. Start index is mid +1. Otherwise, we just keep on looping. If we haven't returned, right, when we're done here, we're going to return a -1. We haven't found it. Same idea here with our iterative binary search, right? We don't need the recursion necessarily, but sometimes it makes our life a little easier. Let's make sure that works. Iterative binary search. Right, don't find it, index 0, 1, 2, 3, 4, 5, 6, right? Looking good. So both ways work. Again, we'll get to the harder cases of recursion next semester. I just want to look at a couple basic ones. And we'll practice a couple in lab as well. We'll have some fun with these. There's some fun ones we can do. Okay? All right, any other thoughts, questions, or concerns? If not, I think we're pretty good. We'll talk about inheritance on Thursday, and then we'll have our lab on Monday. And that will be the last lab that we have. Holy cow. And, it's going by quick, right? Because we don't have a lab after that. Because that's just our final presentations. So really, we're wrapping up the semester here. It's been quite the semester. I've got project 2 graded. I'm working on project 3. I'll get that one in for you. Sorry I didn't get quite all the way caught up here over break, but we'll get those in for you soon. In terms of quizzes, we'll do one last quiz here on inheritance and recursion, and then we'll call that good for quizzes. I think I might have missed 1 or 2 in here. I apologize for that. We'll do one last quiz, and then we'll call it good. Okay? All right, it's been fun, folks. Take care. Let me know if there's anything I can do for you. Feel free to reach out. Don't forget to be working on that final project. We've got time in lab to work on it. We've got some time as well this week and next. Let me know if you're getting stuck on anything, and I'll help get you unstuck for sure. The goal is everyone gets it done. Okay? All right, folks, take care. I'll see you around.